Hello everyone, welcome to Indian School of Physics. Guys, this is very important topic for JEE Mains and Advanced. So here is a short lecture and followed by some PYQs uh, on EM waves. So let's discuss this. So EM waves are mainly produced by oscillating or accelerated charges. And you can say the light is produced or the photons are produced during atomic excitation. All these things we have done, probably you would have done in modern physics. In regular classes I have covered this part. So these EM waves are basically transverse waves in nature. So traveling wave kind of we can write it is a kind of traveling wave. And here electric field vector and magnetic field vector will be perpendicular to each other. So all the time you can see the EM wave will have two components. One is oscillating electric field and another one is oscillating magnetic field. And the wave will be traveling in the direction of vector E cross B. So there can be many possible combinations of EM waves that we will discuss soon. So EM wave travels in the direction of vector E cross B. So you can say velocity of wave is parallel to E cross B. Okay. Another important point which we have to know that E and B will always be in the same phase, and all EM waves will travel with the speed of light in vacuum. In vacuum, they will travel with the speed of light, and we will see its dependency on refractive index also. Now, transverse oscillations of E and B. So it's a traveling wave. We can expect its equation of the form of y equal to a sine kx minus omega t or omega t minus kx. So that we will discuss shortly. They can exert pressure and they can transfer energy and momentum on a surface. So this part we have covered in modern physics, or wherever you are studying there also it would have been covered. The radiation pressure part, it comes in thermodynamics, it comes in modern physics, it comes in EM waves also. Perfectly reflecting, perfectly absorbing surface, all these things. So let's learn how to write equation of EM wave. So I'm assuming here a wave is traveling in positive x direction. So if it travels in positive x direction, so I can assume its equation to be of the form of kx minus omega t or omega t minus kx. Now one thing is clear, if it is traveling in positive x direction, then definitely vector E cross B is going to be parallel to I cap, x axis. So if I'm choosing electric field vector in y direction, then B is going to be in the direction of k cap. So if it is of the form of instantaneous electric field vector, its amplitude sine kx minus omega t. So when we are writing corresponding oscillating magnetic field, first let's maintain the phase sine kx minus omega t. Now perpendicular to this, we have to choose this third vector in such a way that E cross B should come in the direction of I cap. So if I'm taking this as J, then it must be in K cap, and this E naught by B naught will have a fixed ratio, which is omega by K, which is speed of light in vacuum. So E naught by B naught will always be C. Let's take another form here. I'm taking, if any electromagnetic wave is of this form, vector E, this is also representing traveling in positive x axis. So E naught sine omega t minus kx plus phi naught, and it is given it is in the direction of minus k cap. All right, I have to write corresponding B, because sometimes they will give you four options where E and B oscillations will be given, and they will ask you which one represent the correct combination. So first is phase matching. We are doing the phase matching here, and next we have to do is this unit vector E cross B should be parallel to I cap here. Positive x axis we are taking. So if it is minus k cap, then the next vector should be j cap. So this will be the combination of E and B in such a way that we can write the electromagnetic wave equation. There will be multiple such vectors. It is not just one vector. You can rotate it about x axis and you will get infinite combinations of these vectors which will represent the direction of E and B, but it will always be in such a way that E cross B will be along the wave velocity. So it was given to us that it is traveling in positive x direction. Similarly, next form, suppose if they are giving in this form, and they might ask you what will be the B. So E naught by B naught we can write as C. So from there it is known to us what is the amplitude of magnetic field, and similarly here I can write as sine of omega t plus kz plus phi 1. Let's say this is given to you, and it is given it is traveling from here we can judge. Since omega t plus kz is coming, it represent a wave traveling in minus z direction. So first thing is minus z direction. Second, oscillation of electric field is given. Let's say it is given in the direction of j cap. Now I have to choose direction of B in such a way that I should get E cross B as minus z. So let's write the equation of B. So first is B naught, and we know that E naught by B naught is C. So B naught is known to us. Let's do the phase matching. It is representing a wave traveling in minus z direction. So I'm writing omega t plus kz plus phi 1 because E and B should be in same phase. Now J cross I is going to give us minus k cap. So this direction of B is going to be I cap. So this is how electric field and magnetic field components can be written. Both will be written together. If one is known to you and you know the direction of if you know the direction in which wave is traveling, then easily you can write. Okay, now the next part is the optical effects, like polarization is there. It is mainly due to the electric field vector, and it is also known as a light vector. I hope this point is clear to you. It's a small information which I feel everyone should know. Okay. EM wave can form a standing wave pattern in a closed chamber. So let's say a wave is traveling positive x, then after reflection it will go back, and these waves can form a standing wave pattern. And we can observe these EM waves or displacement current concept that I am going to explain in charging of a capacitor. There are few more things which I would like to discuss here. Maybe this place we can add. Okay. Maybe here I can add after this. That's better. Normally question in the past questions have come, so okay, yeah. So this velocity, which is we are writing as c, it is 1 by under root of mu naught epsilon naught. So mu naught and epsilon naught are very known to us. It's like permeability in free space and permittivity of free space. You would have done that already. So in any general medium, it's a refractive index also. It's a refractive index, if you remember, that mu was C by V. This is known to us. Normally people will forget. And in a medium, the same way I can write this speed as 1 by under root of relative permeability and relative permittivity. Like this I can write, and from here I can relate these results. This is, by the way, refractive index. This is a refractive index. It's very likely that one of these questions you will find in the paper. So now I can write this mu as 1 by under root of mu naught epsilon naught, and this will come 1 by under root of mu and epsilon naught. Let's adjust these terms. If we adjust these terms, we are going to get mu and epsilon naught. Okay, we'll have a trouble here, by the way. Let's call this refractive index as n. That is better, because we are already using mu for that. So here it will become mu naught and epsilon naught, so which will become under root of mu r relative permeability. Basically this is dielectric constant. Okay, this is dielectric constant, relative permeability, you can say. This mu r is mu medium by mu. Similarly, I can write epsilon r, which is the dielectric constant. It will be epsilon of medium divided by epsilon naught. This I have already explained earlier in regular classes. All right. So let's move further. Yes, let's discuss this important part here. It's a charging of capacitor, and it's a relation with the EM waves. Okay. So charging of capacitor, when we charge through the wires, the current which is going through the wires is conventional current, which is flowing through the wire. So it is called as conventional current. All right. And through this area in between the plates, we have seen how electric field is present in the capacitor. But if I place one magnetic needle here, then it will show some deflection. It means there must be some kind of magnetic field present in between the plates. Now there is no, basically you can say wires are not present between these two. All right, so let's check here. Magnetic field is observed between the plates of the capacitor as charge increases on the capacitor as a function of time. So it is like charging of capacitor. We'll come to this part. Before that, we need to discuss these four fundamental equations of electromagnetism. You already know about this Gauss law of electrostatics. That is, phi electric is equal to E dot dA in a closed surface, and it is equal to charge inside by epsilon naught. Similarly, there is no existence of monopoles in magnetism. So I can say the integral B dot dA, which is magnetic flux, it is going to be 0 through a closed surface, which is Gauss law for magnetics. Understood? I hope this part is clear, because magnetic field lines are closed lines. So through any surface, any closed surface, whatever number of field lines will enter, same number of field lines will come out. Then this is Faraday's law. We have used this extensively in EMI. So it is like induced EMF, and this is basically Faraday's law, you can say. I hope induced EMF is equal to minus d phi by dt. Everyone remembers that, where phi is magnetic flux. Now we have studied Ampere's law, but here there is a slight change in Ampere's law. We have studied B dot dl is equal to mu naught times I inside. But it has been observed when electric field changes, when there is fluctuation in electric field, then through the medium one current is flowing, which is not flowing through the metal or conductors. In the medium it is flowing, which is called as displacement current, and this displacement current is given by epsilon naught d by dt of phi electric. So if you remember, we have discussed this point also, that if magnetic field is changing, it is generating time varying magnetic field is present, it will generate induced electric field. And similarly, if electric field is changing in space, then it will generate magnetic field. So correct form of Ampere's law in this chapter will become integral B dot dl, which is mu naught times conventional current which is flowing through the wire plus epsilon naught d by dt of phi electric. Let's come back. Okay, after pointing vector, we'll discuss that. So Pointing vector is basically related to energy flow, or you can say in short it is intensity. So it is energy flow per unit time per unit area normal to the surface. This definition we have used for intensity, and this Pointing vector is given by vector S is equal to E cross B by mu naught. And here we have this already we have seen, mu naught epsilon naught is equal to 1 by c square. So let's take one combination of electric field and magnetic field which is forming this EM wave. So here I can write S is E cross B by mu naught, and they are in J cross K. So Pointing vector will be along x direction, positive x axis I cap. So E naught B naught by mu naught, and this will become sine square omega t minus kx. Now if I take average value of this Pointing vector, or average intensity you can say, then it is going to be E naught B naught by mu naught and average of sine square omega t minus kx. Now this average comes out to be 1. We have done that at many places. You would have done in AC also, waves also, right? 11th class. So this Pointing vector average value is E naught B naught. That means electric field amplitude, magnetic field amplitude divided by 2 mu naught, and it comes in I cap direction. Now I have this relation E naught by B naught, which is C. If I substitute these values here, I am going to get this average value of Pointing vector as E naught B naught by 2 mu naught, or half epsilon naught E square times C, or B square by 2 mu naught times C. Now these terms are very much familiar to you. These are energy densities. Energy stored in electric field per unit volume, energy stored in magnetic field per unit volume. So Pointing vector is related to that. So please remember, normally most of the people will forget this C because direct formula might come in the question. So please remember, this is the intensity of light, and it is energy density times C. Any energy density you can take, electric or magnetic, and of course with the maximum value. These are amplitudes here. All right, let's discuss how much energy electric field and magnetic field are carrying. So energy distribution in electric and magnetic field. Now total energy density I can write corresponding to electric and magnetic. This is energy stored per unit volume. So it was half epsilon naught E square, and this was B square by 2 mu naught. We have these relations, well-known relations. So here, if you adjust, substitute these values, you'll find electric and magnetic field will carry equal energies per unit volume, and these values are B square by 2 mu naught, or half epsilon naught E naught square, where B naught and E naught are amplitude of magnetic and electric field. So in one of the PYQ they directly ask this value, and please remember, don't forget this C. I've seen many students making mistake in this part, so just be careful. Next is electric and magnetic field amplitude calculation. So for a point source, direct questions will come on this part, that there is a point source of P naught, and at a distance of R, what is the amplitude of electric field or magnetic field? So it's a very simple, its power is given P naught watts or joule per second. So we can write intensity at a distance of R. This intensity is basically average value of Pointing vector. So P naught by 4 pi R square, I can equate it with the half epsilon naught E max whole square times C, or B max square by 2 mu naught times C. And this I naught is for a point source. We know already that at a distance of R, intensity becomes power per unit area, that is normal to the surface, P naught by 4 pi R square. If you simplify, we can calculate these amplitudes. All you need is just substitute the values. Numerical data can come. It has come in the past. It can come in future also. And similarly, if line source is given, I will write this intensity at a distance of R as P naught by 2 pi RL, where R is the distance from the source and L is the length of the source. So we can equate and we can calculate Emax and Dmax. So this is another simple part. Let's discuss this charging of capacitor and EM waves. So here I'm interested in finding the magnetic field value at a distance of r from this line where through this wire is going, and similarly here at a distance r which is more than the plate area or plate radius. For simplicity, I'm dealing with circular plates of capacitor. So as charging happens, we will see the conventional current in this, due to which charge on the capacitor gets deposited, and inside there is a non-zero magnetic field, and these are the lines along which this displacement current will be flowing through the medium, or you can say in this case it is a vacuum. All right, so charge on the capacitor is known to us. It is charging of capacitor standard formula. Now from here I can write conventional current which is flowing through the wire, which is IC. It is d by dt of QC, so that is also known to us. These are standard formulas. Most of the people will have idea for this. And similarly, electric flux, if I write through this in the entire plate, if I take a surface here, through this surface, E into E is the electric field between the plates, pi a naught square is the area cross section. So this will become Q by A epsilon naught times pi a naught square. So this area and area will get cancelled, and you will get charge as a function of time by epsilon naught. So phi electric is known to us. Now d by dt of phi electric is 1 by epsilon naught dq by dt. Now dq by dt is conventional current. Now this epsilon naught d phi by dt is actually displacement current, which is luckily in this case IC. I hope this is clear to you. So it is appearing as if this thin current is flowing through this cross section. Now they're asking us magnetic field. So magnetic field calculation, we can treat this as a wire. So wire formula we can use for R less than R. For that solid cylinder formula, probably you'll remember. So mu naught I displacement R, basically this formula, mu naught I R by 2 pi capital R square. Most of the people will remember, basically mu naught vector J cross R by 2 by 2, not epsilon naught. Same formula. Similarly for outside, it will behave like a wire. So mu naught I displacement by 2 pi R. All we need is just substitute these values and we can calculate B at a distance of R inside, and similarly B at a distance outside region. Basically this is A naught, sorry. Just make a correction here. Or I'll do that. This less than and this greater than the plate radius. All right. The next part we can take this is your work. You can take it as homework. So basically we must remember wavelength or frequency range for all EM waves. This spectrum will involve X-rays, it will involve ultraviolet, then visible range, then radio waves, all those frequency and wavelength range. You should have some idea. Any one you can remember, others you can find. Now in this part, this PDF is there. You can go through this. However, theory I have completed, but still you can always give one look. And there are all these PYQs. You can go through this, and it's an important topic and it's a scoring topic. But I'm very sure with these pages, just first few pages, whatever I have discussed here, you'll be able to solve every single problem of PYQ. And do let me know if you are comfortable after going through all this. So that's it in today's video. It got delayed because of lot of disturbances at my end. So apologies for that. I hope your preparation is in full swing. So all the very best for the mains. Thank you.